Lesson 3.5, Exponential and Logarithmic Models. Alright, we've already had exponential growth and decay. When we talked about it before, though, was y equals a, b to the x for both of them. And it was growth when the base was greater than 1, and it was decay when the base was between 0 and 1. Well, here we've rewritten it with e, the natural base, for our models. And it works the same. It's just the base e is more useful for calculus, so often the models have the natural base. So let's suppose a population is growing according to the model p equals 800 e to the 0.03 t, where t is years. What is the initial size? Well, the initial size is when time is 0. Well, that'd be e to the 0, but e to the 0 is 1, so it's just 800. So that number, the number in front of the exponential part, is your initial size. So it's 800 members. And how long does it take to double? Well, if it started with 800, when we double, we'll have 1600. So we'll let p be 1600. So to solve, we'll get the exponential part by itself first. So 1600 divided by 800 is 2. And so now we have this nice little exponential equation. To get rid of the base e, we have to do the opposite. So the opposite is a logarithm. I'm going to do log base e. And then finish by dividing. So log base 2 divided by 0.03 is 23.1. And t was in years, so 23.1 years to double this population. A common use of exponential functions, especially exponential decay, is radioactive decay to measure, for example, how long things have been buried or how long since they died. So our basic model is the exponential decay, but for radioactive decay they changed some of the letters to give it different meanings. So instead of y, we use A. A is the current amount, so this is current amount. A0 is the initial amount, and K is the constant. We often talk about half-lives. Half-life is the time it takes for half of the material to decay. And so each different radioactive material has a different half-life. So if we know the half-life, theoretically, we could figure out how much time between when it started decaying and the current. It's often used in carbon-14 dating, C14 dating. Carbon-14 naturally occurs in the atmosphere, and we all breathe it in. All living things take in this carbon-14, which is radioactive, and has a useful half-life, reasonably short half-life of around, I think it's 5,000 years. So then, using this model, they can date things that are old, that have carbon in it, that were once living. It'd be living things, so plants or animals. Only it's not quite so simple, because we have to know the initial amount. Well, we weren't there. We don't know what the initial amount was. So they make an assumption that it's similar to what it is now. Oh, but wait, with more industry and burning of fossil fuels, there's a different amount of carbon-14 in the atmosphere than what there used to be. So what they've done is they've taken things that have known dates, so like documents, paper documents or papyrus documents that have the date written on it so we know what date it is, and they make this curve. So what they do is they use the model and get a result from the model, and then they have to use this graph to figure out what time it actually is. And you can see, let's say we had this line. Well, it hits 3 places. So it could be any of those 3 places. So you don't really know. You have to make it kind of a guess. And once you get before historical documents, it's just guesswork on the scientist's part. So it's useful, carbon-14 is useful for a historical period when we can calibrate it with known dated documents, but before that, the assumption about the initial amount of carbon-14 is just an assumption and can throw off the actual dates. Let's say carbon-14 has a half-life of 5,700 years, which is about true. If a sample starts with 3 grams of carbon-14, how much will remain after 100 years? So we'll use our radioactive decay formula. And the first thing we have to do is find the K. All right, so it says we're starting with 3 grams. And we're going to use this half-life. Half-life is the amount of time it takes for half of it to go away. So if we start with 3, half of it left would be 1.5. And our T is the half-life in years, that 5,700. So we solve this to get K. So we'll divide by the 3, which gives us 1/2. And then this is an exponential function. So we get rid of the e by taking the natural log of both sides. Solve exponential equations with a logarithm. Divide by the 5,700. So by the way, the K is always natural log of a half divided by 5,000, or divided by the half-life. So our K is approximately negative 1.216 times 10 to the negative 4. So now we can write our model again. A equals, we're starting with 3, e to the K times our time. All right, our time, it says, is 100 years. So we'll plug in 100 for our time. And we run that whole thing through the calculator, and we get 2.97 grams, which isn't much different from our 3 grams, but it's only 100 years compared to the 5,700 for half of it to go away. Our next model is the Gaussian model, known as the curve, which describes a normal distribution. That is the function. On this curve, the highest point there will give you the average. So in my particular graph, the average is 2. And then you see it goes down on each side. This is used to model anything that is normally distributed, such as SAT scores, or heights, or weights, or pretty much anything that is naturally occurring can be modeled with a Gaussian model. Next, we have a logistics growth model. which is used for a fair model of population. So population starts pretty level, and then it has a quick increase, but then we start having pressures like not enough food or space or whatever, and so the population growth slows down and then levels out, and it levels out at what is called the carrying capacity, which is the maximum population that can exist in that habitat. And the model, the equation, is that. Our last model is the logarithmic models. We can do it with natural log or the common log base 10. Two uses of these. The Richter scale for earthquake magnitude uses a log base 10 scale, which means each number up on the Richter scale, so you have a 7 and then an 8, is 10 times more powerful. Decibels are also a log base 10 scale, and they measure the loudness of sound, which actually better models how your ear perceives the sound than something like a linear model.